Hi everyone, my name is Sarah Jacobson. This semester, I conducted research under the supervision of Dr. Stanley Pierre Ngay, my mentor, on the topic of the synthesis and thermodynamic properties of potassium 2-methylbutanoate. In this study, I aimed to synthesize and determine the thermodynamic functions of potassium 2-methylbutanoate and also to determine if it exhibited any solid-solid phase transitions, which were exhibited by its straight chain homologs. If it did have these transitions, I wanted to see if the temperature at which they took place was affected at all by the branching created by the methyl group at carbon 2 of the compound. Solid-solid phase transitions are a type of first-order transition in which one solid phase transitions to another solid phase. These transitions take place isothermally, meaning that there is no temperature change accompanying them. A solid-solid phase transition will commonly occur in nature under anisotropic pressure, meaning that the pressure doesn't have to be uniform or constant for this transition to take place. A mechanism for solid-solid phase transitions has been proposed where the compound very briefly melts to form a metastable liquid intermediate before entering a more stable crystalline state. Phase change materials, or PCMs, are good storage materials for solar and thermal energy because of the isothermal nature of the transitions which they undergo. They can isothermally store heat at the temperature where these transitions take place. An understanding of certain physical properties of the metal alkanoates is important for the analysis of their thermodynamic properties. In general, organic salts have an inorganic ion, which in this case would be the potassium cation, and an organic counterion, which would be the 2-methylbutanoate anion. These arrange to form a lamellar crystal structure, meaning that the layers of ions stack on top of one another like this. Certain modes of movement within the molecule can affect the lattice heat capacity of a metal alkanoate compound. These modes of movement include hindered rotation, carbon-carbon bending, carbon-carbon stretching, and the bending, wagging, symmetric, and asymmetric stretching, rocking, and twisting of the methylene groups in the carbon chain. The reaction studied in this research study is between 2-methylbutyric acid, which is a carboxylic acid, and excess of potassium carbonate to form a carboxylate salt, potassium 2-methylbutanoate. The salt solution was then concentrated using a rotator evaporator, or Rotavapor, which is used to distill off solvent and increase the concentration of the solution. Thermal analysis was conducted using Differential Scanning Calorimetry, or DSC. In this method of thermal analysis, you have a reference sample and a sample whose thermodynamic properties you want to measure. Heat is applied to both of them, and the rate of heat flow to each is measured. This is conducted in a calorimeter, which ensures that the environment in which the analysis is taking place is one in which you can control the rate the temperature changes. DSC is advantageous for thermodynamic analysis. However, it's also limited by certain gaps in understanding of the underlying theory created by disagreements within the scientific community. Also, when you take simultaneous measurements, it slightly lowers the sensitivity of the instrument, but ultimately does not show a substantial decrease in the accuracy. The first synthesis trial was conducted to gain familiarity with the methods to be used. Potassium carbonate was dissolved in methanol, anhydrous, and then 2-methylbutyric acid was added. The solution was reacted in a reflux apparatus shown on the top left of the screen for 5 hours, and then it was filtered while the solution was still hot to remove any excess potassium carbonate. A Rotavapor R3000, shown in the bottom left of the screen, was used at 20% rotation and 40 degrees Celsius for 2 hours. When this trial was conducted, the round bottom flask used had too small of a neck to fit onto the Rotavapor, so an adapter was necessary. Unfortunately, what happened was that as the solution heated, it created pressure within the flask, which caused the flask to slip off of the adapter and pick up some water from the Rotavapor. This introduced a contaminant into the sample. The round bottom flask was then heated until all of the methanol and about 1/3 of the water had evaporated out. This concentrated the solution so that crystals could begin to form. The sample was then refrigerated overnight to allow more crystals to form, and it was filtered using vacuum filtration via a 2XZ1G vane vacuum pump, shown in the picture on the right, and a new Buchner funnel. The crystals were washed with anhydrous 2-propanol, and then lab-grade methanol was used to recrystallize them. The solution was heated, and the solvent was evaporated until the solution was very saturated with crystals. The evaporation was allowed to stop only when there was a very thin layer of methanol left on top of the crystals. The crystals were then filtered using vacuum filtration. The crystals were now pure, and so they were placed in a test tube, and inside of the test tube was placed a rubber stopper with a glass tube running through it. The glass tube was attached to the vane vacuum pump once again to dry the crystals, as shown in the picture on the left. A Digimel MPA 160 melting point apparatus, shown in the pictures on the right, was used to determine whether or not the compound would melt below 250 degrees Celsius. The sample was then subjected to the 2XZ1G vane vacuum pump once more to take out any water vapor that had been absorbed when the sample was exposed to air. The glass tube was then sealed with parafilm and the sample was stored. A second synthesis trial was conducted using a new reflux apparatus, shown in the picture on the left. This reflux took place for about 4.5 hours. This time, a round bottom flask that was large enough to fit onto the Rotavapor without an adapter was used. The solution was then filtered while it was hot using vacuum filtration so that any excess potassium carbonate would not remain in the solution. The Rotavapor R3000 was used once again, this time at 30% rotation and 80 degrees Celsius to increase the concentration of the solution. During this run of the Rotavapor, a vacuum was applied, which decreased the vapor pressure of the solvent and therefore increased the evaporation rate. The concentrated solution was then filtered to isolate the sample, and then this was dried using the 2XZ1G vane vacuum pump in the same method used with the test tube in the prior sample. For thermal analysis, the samples needed to be prepared before they could go into the DSC. An aluminum sample pan, like the one shown held in tweezers in the photo on the left, was crimped with the sample inside of it using a SSC30 sample cell crimper, which is shown in both photos. 2 empty aluminum sample pans, one serving as the reference and the other acting as the sample, were crimped using this instrument before they were run in the Shimadzu DSC50 to establish a baseline. A very small quantity of sample 1 was placed inside of another aluminum sample pan, covered, crimped, and analyzed. The melting point was then taken in the DSC. The sample holders of the DSC were then cleaned using acetone and toluene. The DSC-50 used during this experiment is shown in the pictures on the left. The DSC was then programmed using the temperature programming software included in the instrument, and a test run was done to ensure that there was no contamination present on the thermal stages. The test run went from room temperature to 450 degrees Celsius. However, an anomaly was observed at 450 degrees Celsius, so another test run was completed to ensure that the anomaly was no longer present. Indium was then used to calibrate the DSC-50. Although the first sample was contaminated by an unknown orange substance found in the Buchner funnel at the time of filtration, recrystallization was sufficient to purify it, and it yielded a generous amount of crystals. There was enough present for thermal analysis in the DSC-50. During the synthesis of sample 2, it was discovered that adding a vacuum to the Rotavapor drastically increases the rate at which the solvent will evaporate out. During the preparation of the DSC-50, a baseline was obtained using the sample pans, as I previously mentioned. As the figure on the slide shows, a straight line in the temperature range of interest was obtained following the initial cleaning. A straight line indicates that the DSC-50 was clean enough for sample analysis. Melting thermograms were obtained for both samples. Both of the thermograms agreed. The thermograms show that the samples began melting at 184 degrees Celsius and finished at 218 degrees Celsius. There is a small endothermic peak observed at approximately 90 degrees Celsius, as shown in the figure on the slide, but this corresponds to the boiling point of acetone, which was used to clean the thermal stages before the samples were ran. There was also a peak at approximately 360 degrees Celsius, which could indicate the presence of a phase transition. Further investigation is needed to confirm these findings. The line produced when the thermogram turns and proceeds from right to left indicates that the sample had begun to cool at that point. This research demonstrates how the synthesis method previously used by Dr. Ngay and his associates to prepare other metal alkanoates can also be used for potassium 2-Methylbutanoate. These methods produced a large enough sample size for thermal analysis in the DSC-50. The melting point of the compound was found in the DSC-50 to be 184 degrees Celsius. However, the sample did not melt at this temperature in the Digimelt MPa 160. Therefore, further analysis is needed to determine if human or instrumental error was a factor in this discrepancy. There is no current literature value known for the melting point of potassium 2-methylbutanoate. I had originally planned to take the heat capacity, Gibbs free energy, entropy, and enthalpy of any transitions which I observed. However, due to the coronavirus pandemic, data collection was not completed, and I was unable to finish my analysis. Therefore, further research should be conducted, and this study should be completed. To do so, I would suggest that the purity of the desired sample should be determined using the purity determination software available in the DSC-50. Also, Dr. Ngay recommends Fourier transform infrared spectroscopy, FTIR, and proton nuclear magnetic resonance, proton NMR, be conducted as adjuvant purity determination methods. A small and broad exothermic transition obtained at about 360 degrees Celsius may indicate a solid-solid phase transition, as I previously mentioned. This transition should be further investigated. Plots of heat capacity versus temperature should be prepared for each of the samples to examine for solid-solid phase transitions, and other thermodynamic functions such as the enthalpy, Gibbs free energy of transition could be calculated from these plots. Finally, future research may also be conducted on similar branched potassium metal alkanoates having longer carbon chains and those with multiple points of branching. This will help to serve as the next step in the long-running study which Dr. Ngay has been conducting over the years. Finally, I would like to dedicate this paper to those who taught me, guided me, advised me, fed me, and laughed with me throughout this process. I am blessed to know each one of you.